Yes.
Everything's good?
Yes, thank you very much.
Thank you.
Thank you. Okay, our next distinguished speaker, Dr. Michael Norman, is an Argonne Distinguished Fellow and the Director of Argonne Quantum Institute. He has been a Fellow of American Physical Society since 1995 and received the University of Chicago Distinguished Performance Award in 1999. Previously, he was the Director of Material Science Division at Argonne and has served a number of roles over the years, including the editorial boards of Physical Review B and Physical Review X. He is the condensed matter physicist by training with 276 publications today. The title of his talk is What is Quantum Spin Liquid and How is Related to Quantum Computing? Dr. Norman, thank you very much for your time. Please go ahead.
Yeah, thanks a lot. When I was originally contacted by the organizers for this kind invitation, um, I really didn't know what to say. Although director of the Argonne Quantum Institute, I'm not really a QIS person per se. And so I told them, well, I had a quantum summer school last year where I talked about the relationship between quantum spin liquids and quantum information. And they thought, okay, well, this could work. If it's sort of outside your area of expertise, I think it was an opportunity to learn something, or as Monty Python used to say, now for something completely different. So some of this is talked about in a review article I did with 5 colleagues that was published in Science back in 2020. The picture is Herbert Smithite, which is a candidate quantum spin liquid, but I don't really have a chance today to talk about real materials. So let me start out with some elementary slide. We know electrons behave like little spinning tops. They can be thought about as little bar magnets with the north pole either pointing up or down. Um, we call this spin up and spin down, and we know that these can be manipulated by Pauli matrices. The Z matrix basically reads off the spin eigenvalue, and the X and Y matrices basically interchange spin up and spin down, either with a unit phase or with a phase of I. And that rotates you around the so-called block sphere. You can think about interacting spins. They have, and you'll see the connection with quantum computing later because, of course, spins can be mapped to qubits, as you saw from the block sphere on the previous slide. But they have analogous phases of ordinary matter. If the spins all have a fixed orientation, we call this long-range magnetic order, and that's an analog to a solid phase of matter. They can have a random orientation, which we call paramagnetism, and that maps onto the gas phase. Or you can have something which we call a melted magnet, which is the analog of the liquid phase. So a quantum spin liquid is a melted magnet that's melted because of quantum fluctuations. Um, Although no long-range magnetic order is present, each spin knows about what all the other spins are doing. And therefore, this is an example of something called topological order. For those of you who heard of the fractional quantum Hall effect, that's another example of topological order. So it doesn't have order in the Landau sense, but it has order in a more formal mathematical sense. This is an old problem going back to the foundations of quantum mechanics back in the 1920s. There was an original model introduced by Werner Heisenberg and worked on by other people like Dirac. The Hamiltonian is taken to be just a dot product of the spins at neighboring sites, I and J. So the spins are vectors. J is the exchange interaction between the spins. And for a ferromagnet, J is less than 0, so the spins want to be aligned. And so this is sort of a well understood problem. This is, how your refrigerator magnet works, for instance. But then what happens if J has the opposite sign? And therefore the spins want to be anti-aligned. This is a problem of antiferromagnetism. And there's a controversy there. So we know what happens when we only have 2 spins. We know that if the exchange interaction is positive, the spins want to align in a singlet, up, down, minus, down, up. Whereas if they're want to be aligned, we call that a spin triplet state. That's for exchange interaction less than 0, and therefore you get the up, up, down, down, or up, down plus down, up. So when Nell proposed that you would have a lattice of alternating up and down spins, people were uncomfortable with this because you can see that this state is not an eigenstate of the spin operator. That is a linear combination of spin 0 and the SZ equal 0 component of the spin 1 state. And so this bothered a lot of people. And so the way to think about this is if you look at the cross term, the SX and SY terms in the Hamiltonian, these can be written as raising and lowering operators. And of course, if you apply this to the fully polarized state, which is a ferromagnet, it doesn't do anything. But of course, if you apply it to an up-down state, these terms flip the spins, and therefore, as you apply these terms, they should quench the spin. And in fact, Hans Bethe showed back in 1931 that this is in the one-dimensional case, the ground state is a chain of spin singlets rather than this up-down state of Nell. But we now know, of course, Nell was proven right in 3 dimensions. This was shown by neutron scattering after the Second World War. And this is an example of spontaneous symmetry breaking. And so antiferromagnetics have become ubiquitous now. People are starting to use them for things like spintronics applications. But the original problem existed. Is there something else besides this Nell state where the spins would alternate up, down on some sort of checkerboard lattice? That is, why don't you have singlet formation like you have in the one-dimensional case? And lots of people have thought about this. People like Landau, Pomeranchuk, and Phil Anderson himself. So this led to a paper of Phil Anderson's in 1973 that said the following. Maybe the singlets do win out if you have a non-bipartite lattice, like a triangular lattice, where you don't have like square lattice, which you can sort of divide into 2 sublattices. And his proposal was that a liquid of spin singlets would win out over this ordered Nell state. So the ideal to think about is if you have a triangle and the spins are opposite on 2 of the corners, the third corner doesn't know what to do. It's sort of schizophrenic. It doesn't know whether to point up or to point down. But it turned out not to be quite the case. David Hughes and Veit Elser showed in 1988, in fact, that this 120-degree state shown on the right wins out. That is, the spins are oriented 120 degrees relative to one another, and that state wins out over this so-called spin liquid state. But the energies are very close, and people have now since then looked into this, and small additions of Hamiltonian like ring exchange or longer range exchange interactions can actually stabilize a spin liquid. So what you want to do is look for a lattice which is more frustrated than the triangular lattice. And the greatest example of that is something known as a kagome lattice. This is named after a form of Japanese basket weaving. This is where you take a triangular lattice and remove a quarter of the sides. And so when you remove sites, you get hexagons instead of triangles. And the coordination number on this lattice reduces from 6 neighbors to 4 neighbors. And that tips the balance where a spin liquid state should win out over a Nell state. So what is this resonating valence bond liquid? The ideal is the fact that imagine you have a lattice of singlets. That is, the 2 sites are paired into a singlet state. And then these singlets resonate from one bond to the other. So the ideal Phil got this was from Linus Pauling at Caltech, who had proposed this to describe what was going on in benzene molecules. And so the ideal here, though, is the following. The superposition you see is a plus sign. So each of these configurations goes in with the same sign. And so what we're representing here as a wave function is because of this, all of these configurations are coherent, and therefore you have some sort of coherent long-range order over the system, even though you have no long-range order in the Landau sense. So it's not symmetry broken in the Landau sense, but you still have this sort of long-range order, which turns out to be topological in nature. So you can see this really clearly if you look at exact diagonalization studies of small clusters. So people have done this in a variety of cases. So in the left case, I show a square lattice. And what you're showing is a ground state in each spin sector. So obviously, if you have a finite cluster, then beta is right. That is, the ground state is spin 0. And if you look at the lowest lying states, spin 0, spin 1, spin 2, it sort of forms like a diagonal line. And in the infinite thermodynamic limit, this line becomes flat. And therefore, that's the spontaneous symmetry breaking that leads to the null state. And so the null state can be thought of as a linear combination of spin 0, spin 1, spin 2, etc. As you can see from the middle graph, the triangular case looks very similar to the square lattice case. That is, you have a ground state manifold, and then above that, you have these red crosses, which represent the low energy magnon states. And then after that, you have the continuum. If you look at the kagome lattice, you can see it's extremely different. You don't see anything like what you see in the square and triangular case. You see an array of energy levels coming all the way down in energy, with, of course, for a finite lattice, the spin 0 states lying lowest in energy. So we know that the kagome case is very, very different from the square lattice and the triangular lattice case. And all indications is that this exotic quantum spin liquid case is indeed realized in kagome lattices. But the problem is the exact diagonalization studies are limited to 48 sites because the size of the problem goes like 2 to the n, where n is a number of sites. So this is a problem. And those studies so far are inconclusive. We don't know whether the excitation spectrum is gapped. We don't know if it's gapless. We don't know what kind of spin liquid it is. There are some indications from the exact diagonalization studies that you may even be breaking inversion symmetry. And so to go much beyond 48 sites would require a quantum computer. And the reason, of course, is that in the problem, you can match each spin to a qubit. And so this is sort of the first touch base with quantum computing, is that if we actually had a functioning quantum computer, that had 100 logical qubits, we would be able to tell us much more about this problem than what we know right now. So this is sort of the first place where quantum computing sort of comes in. Okay. What are the excitations about this spin liquid? They're not magnon states like you get in an ordinary magnet. And what happens, of course, is you can break a singlet up into 2 free spins, and we call these things spin-ons, or Phil called them spin-ons. And that's one kind of excitation. The other excitation is that you can take, say, a string on the right going from A to B, and every time the string crosses a singlet, you just change the sign of the wave function from plus to minus. This is a kind of singlet excitation that's called a vison, because vison sort of means vortex. And I'll explain why this looks like a vortex in a minute. But that's the ideal, is that the excitation space of this materials have free spin-ons and free visons. And I'll talk about why this comes into play for quantum computing in a moment. So there have been numerical studies using approximate techniques. This is a density matrix renormalization group calculations, which were done by Steve White, who's just down the road from Caltech. And their results said that the material is a gap Z2 spin liquid. I'll explain what a Z2 spin liquid is in a moment. But for those of you who know quantum computing, it's isomorphic to the toric or surface code. And it looked like in that case, you basically have a melted you had a diamond valence bond solid, which is basically a lattice of singlets, which melts. So this is what it looked like. But there are other DMRG studies where they do these calculations on a cylinder, and they sort of twist the cylinder. And by twisting the cylinder, you can move your finite mesh around. And the claim is when you do that, you have evidence that you have a Dirac cone. That is, the excitation spectrum is Dirac-like, and therefore you have what's called a U1 spin liquid rather than the Z2 spin liquid. So again, numerical studies are inconclusive. Some say gapped Z2 spin liquid, some says a U1 spin liquid. So what are the challenges here? The challenges are that exact diagonalization studies are currently limited to 48 sites. Exascale computers can buy you some more, but a quantum computer will ultimately be needed to solve these kinds of problems. You say, well, why don't you use quantum Monte Carlo? The problem with quantum Monte Carlo is because you're dealing with fermions, you have the so-called sign problem that inhibits Monte Carlo calculations to be done on these kind of materials with any kind of rigor. And then there are these various tensor methods that are based on quantum information sciences type ideals, density matrix renormalization groups, protected entangled pair states, multi-scale entanglement renormalization ansatz. All have been applied, all typically give different results. And there's an implicit bias in these simulations. They typically bias yourselves to low entanglement states, and the cost rises very substantially as you increase the number of variational degrees of freedom. And then we have the other problem is if you want to map to real materials, you need to know what the parameters are in the real materials. That involves electronic structure methods. And as you all know, that quantum computers, one of the things that they could possibly do is help you get more accurate electronic structure methods and therefore more reasonable microscopic parameters that we would define for real materials. So here's the connection with quantum computing. There's a famous paper by Kitaev going back to 2000 that was published in 2003 about fault-tolerant quantum computation based on anyons. And the example he gave is imagine I have a lattice of bonds. And on these bonds, I'm going to have either take a product of four poly X matrices, which are the red cross you see in the upper left, or I'm going to take a product of four poly Z matrices around a square, and that's a blue square you see on the right. And the Hamiltonian actually consists of star operators and placket operators. And in the ground state, all of these operators have unit value. They commute with one another, and therefore this problem can be solved exactly. And we know this problem is a toric code. It turns out the toric code is isomorphic to the Z2 spin liquid that I mentioned earlier that people think may be the ground state of this kagome model, and is also the basis for the surface code. So the way you get excited states is you flip the signs of some of these bonds. You flip them from plus to minus, and you get two kinds of excitations. One we call electric anyons, and the other one we call magnetic anyons. So these are called E particles, and they're M particles. They're basically gotten by simply reversing the sign on some of these bonds. And these things are the excitations about the ground state. And these E anyons are no more than the spinons that I talked about before. And these M anyons are no more than the visons I talked about before. And now you can see why we call the vison a vortex excitation. It corresponds to a square loop on the lattice, which sort of defines a vortex inside the placket. And you can extend this to 3 dimensions. This has been done by people. And then, like I said, this is an example of a Z2 spin liquid. Ground state has all star and placket operators with +1. E anyons reverse the sign on one of the stars. M anyons reverse the sign of the wave function on one of the plackets. They can only be created in pairs, and both involve an excitation gap. So this is an example of what we call a gap spin liquid. In this case, a gap Z2 spin liquid. Okay, and so this is a connection. The kagome problem that Steve White and them solved, right, is isomorphic to this toric code model that people now use for fault-tolerant quantum computation, because you can map the toric code. The toric code is a precursor to the surface code that people use for logical error correction in quantum computers. And just to mention, on the torus, the ground state has fourfold degeneracy. And the importance of this is the following: because you have a gap in the excitation spectrum, this fourfold degeneracy is protected. And therefore, people now have proposed that these kind of systems could be used as a basis for topological quantum computing, because the code space, which would be this ground state manifold, will be protected by an excitation gap from the excited states. And therefore, one could potentially use this as an example for topological quantum computing. And of course, this is an approach that Microsoft has taken to construct a quantum computer. The interesting thing to think about, though, is if you're in a Z basis for the spins, then in the objects in the X basis is non-local and vice versa. Therefore, these models have long-range entanglement. That is, That is, although the star and placket operators commute with one another, each has a non-trivial impact on the other that extends across the entire system. That is, a spin on one side of the system knows about a spin on the other side of the system, and therefore we have long-range entanglement, and we have an example of what we call topological order. These E and M ions have mutual statistics. If you exchange, so just back to Pauli exchange statistics. If you exchange two integer spins, you get a phase of +1. If you exchange two half-integer spins, you get a phase of -1. We call the first object a boson. We call the second object a fermion. What happens if we take one of these excited state particles from a spin liquid, the E ion or the N ion, and we exchange it with one another? Their self-statistics is +1, so they act like bosons. But if we encircle an E ion around an M ion, then the phase is -1. So their mutual statistic is -1, like a fermion. So the product of the two is like a fermi. So the product of an E ion and M ion behaves like a fermion. So the importance of this thing, of course, you could take an M ion and move it to the other side of the system. It doesn't matter how far away from it is. If you encircle it around the E ion, you pick up a phase of -1. And therefore, this is again another example of the long-range entanglement properties of the system. And this, of course, like I said, is what Microsoft is trying to exploit for purposes of topological quantum computing. And you get these fusion rules that if you multiply two E ions, you get unity. If you take an E ion and multiply it with an M ion, you get a fermion, etc. And you can now see where this topological degeneracy is coming from. If I create a pair of ions, I wind it around a torus and annihilate it. I can do the same thing with an M ion pair, and I have two non-trivial loops on a torus, and so it turns out the ground state degeneracy is 4. And in the topological quantum computing space, this defines my code space. So as I mentioned, what does it have to do with quantum computing? The Toric code is an example of a surface code. These star and placket operators are what people call known as stabilizers. Their values of ± ±1 can then be used for error detection. And therefore, you can take an array of these things where you have measurement qubits and data qubits. You can define these X and Z operators. If they're supposed to be +1 and you turn out that one's a -1 instead, you know what errors occurred, then you can try to correct it. And therefore, these arrays define logical operators. We call them X and Z logical operators. And people now implemented this. And if you do this on the Willow chip for Google, you can find out as you increase the number of qubits, even though you would say the error rate should go up, you're increasing the number of physical qubits. They've been able to show that the logical error rate goes down as you increase the number of the dimension of the surface code. And therefore, people are now seeing the exponential scaling that you need to make fault-tolerant quantum computing happen. So these things have been, this Toric code has been actually also simulated on a quantum computer. This was done on the Google Sycamore chip, published about 4 years ago. The crosses are the qubits on this map. The blue squares represent Z operators that have +1, and they're the analog of the stars of the Toric code. The purple squares are X operators. They're plackets, and when they have a +1 eigenvalue, they're purple, and they are the analog of the placket operators. And therefore, the Toric code can be prepared by taking a trivial array of qubits. You just apply a series of Hadamard or CNOT gates, and then you can use this, and you can prepare the Toric code ground state. And then once you prepare it, then you can apply various X and Z gates and create pairs of anyons and pairs of visons, and you can move them around each other, right? And then you can see, do I have the right topological phase as I move one around the other? The answer is yes. Do I have long-range topological entanglement entropy in the system? And the answer is yes. And so all this has been tested on this Google Sycamore chip, and it all more or less works out. So you can see all the mutual exchange statistics, the statistics between the E ions and the M ions, exchanging the two, creating fermions, and then, taking an E ion and moving around a fermion and all of this kind of thing. and you see exactly what the theory predicts. And now again, you can take arrays of these guys. You can take, say, a 4x4 array, and you can define X logical operators and Z logical operators, and therefore you can do logical quantum computing, which they demonstrated on this thing. And then later with the more accurate Willow chip, they showed that you can in fact get exponential suppression in the error rate as you increase the size of these arrays. Now, the Toric code is not a universal gate set for quantum computing, but it can by introducing defects in the lattice by using Y gates instead of X gates and Z gates. And this leads to what we call non-abelian anyons. And these have been simulated on the Sycamore chip as well in this paper that was published 2 years ago in Nature. The ideal is you put defects on this lattice, and then these defects behave like non-abelian anyons. And so the way you do this is that if you do a product of an X and Z gate, of course, this is a Y gate. And you can use that for introducing defects. And if you take these defects around each other, you will notice that you get a very general fusion rule. If I take two of these anyons, they can either annihilate to the vacuum, or they can annihilate to a fermion, or they can combine to form a fermion depending on the path history as you take one around the other. And therefore, because of this, you have this non-trivial code space. You have unity, or you have the fermion operator, and therefore you can move around in this code space. And because you now have a matrix that you're defining here, this then allows you to do a universal gate set. And like I said, these kinds of objects have been created on the Sycamore chip and manipulated as you want. And you can also do something even more exotic. This is a paper that was published last year by Quantinuum. What they did was they took a kagome lattice and they put a different kind of toric code in this kagome lattice, which had described by a D4 Lie group. And this object has 22 different anyons in it, not the 2 in the toric code, but actually 22. And the way they got this is they took 3 toric codes and basically stitched them together. So on the kagome lattice, you have a series of corner sharing triangles. You have green sites, you have red sites, and you have blue sites. And then what you do with these sites is you define a toric code for the green sites, a toric code for the red sites, a toric code for the blue sites. And then you put terms in your Hamiltonian that allow these 3 toric codes to interact with one another. And you do this with these so-called 12-body star operators, which are basically formed by products of X gates and CZ gates. And you do this by tying it together, and you can create all sorts of weird anyons. In this case, there's 22 of them. You have blue, red, and green M anyons. You have blue, green, and red E anyons, and then you have a bunch of other excitations as well. And you get much more complicated fusion rules that if you take 2 M blue anyons and annihilate them, you can get one of 4 different states, either the vacuum state, an E red anyon, an E green anyon, or the product of the 2. And you can do all sorts of weird things. Here's an example where they braided 3 sets of these things and you form something called Brownian rings. And this was all done on the Quantinuum trapped ion processor. So let me go back to the beginning. So what does all this have to do with the Kagome-Heisenberg model that has a long history going back many, many decades? The ideal is that people have now finally gotten to do using a quantum computer to do finite clusters. And the latest was by Bert DeJean's group in Berkeley. The first author now works for Google. They looked at a system where you had 12 sites on it. We know what the exact diagonalization ground state for this. You should get a pinwheel state, which is shown on the left. That is a pinwheel of singlets around this star. And this is exactly what they found in their quantum computer. So once we get a better quantum computer where we can go beyond 48 spins and beat the current limit of exact diagonalization on classical computers, the hope is that this old problem that has roots going back to the foundations of quantum mechanics, we might be able to solve with a quantum computer. So if you didn't follow everything, I think the ideal is that there is a fundamental connection between spin liquids and quantum computing. The tie-in is a toric code, but there's many other examples. These anyons, again, are the basis for what Microsoft is trying to do with their topological quantum computer. And then to turn the problem back around again, in the end, we hope that we can use a functioning quantum computer to solve some very tough problems in physics that have been around for the last 50 years. So with that, let me bring my talk to a close. Thank you.
Thank you very much, Dr. Norman, for this great presentation. Maybe we have time, a little time for short questions, one or two. Any question from the audience or from the chat? So we can also look at the chat. Any question from, yes, go ahead. Right, two questions. Can you come, maybe you can come here if you want. Can you hear?
No, not it.
Okay. Yeah, sure. You can come over.
Hello, can you hear me okay?
Sure, absolutely.
So is the main utility of the isomorphism between kagome spin liquids and toric codes, is the main utility of that you could use toric codes to simulate kagome spin liquids, or that you use kagome spin liquids as toric codes for computation?
Yeah, so I didn't have it because I only had half an hour, right? So some people may know that there was another paper, right? There's a simplification of the Kagome-Heisenberg model, which is called the dimer model, where you put a bunch of hardcore dimers on a Kagome lattice. This was solved by Misha Lukin's group at Harvard, and by using a neutral atom quantum computer. And that paper was actually published at about the same time as a Sassinger paper that was using the Google Sycamore chip to simulate the toric code. So the toric code is sort of isomorphic to the Z2 spin liquid on a Kagome lattice, but they're not identical. So what these guys have done is a simplification of the Kagome-Heisenberg model, which is called a dimer model. But you raise an interesting question. Has anyone really tried on one of these platforms, to do something like try to solve the Kagome-Heisenberg model? And the answer is, besides, some work like the one that Bert de Jong did, the answer is no. It's one of these things to be done, so to speak.
Are there any major technological hurdles for why that hasn't been done, or?
Yeah, I mean, I could go into lots of examples, right? I mean, one of the issues, of course, with things, if you look at the Google Sycamore chip, right, you have a square lattice. So this is why it's very amenable to the toric code, which you sort of define as bonds on a square lattice. The Kagome lattice is a triangular lattice with holes in it. So probably this is why those guys with the continuum were able to do it with their trapped ion array, because in trapped ion array, you can move ions around and reduce for any geometry you want. Same thing with Misha Lukin's group. They could only do the dimer model because what they were using was Rydberg states, right? So you excite Rydberg state, so the ground state, is a ground state, and then you would excite it and get the Rydberg state. And now that forms your dimer bases. And it's not equivalent to the Kagome-Heisenberg model, which is a little more complicated. So the mainly thing is, like you said, it's just technological limitations of the machine that you're using to exploit to try to solve the problem. That's the first problem. And of course, the other thing is there's error, right? The error rates on these NISQ machines are pretty high. And so typically what you should do is run the things over and over and over again and get some sort of statistical ensemble.
All right, thank you.
Thank you for the next question.
Hello?
Hi.
Do you think you could possibly simulate in an anisotropic spin fluid, you simulate a resonant liquid spin fluid using a Markov process? Or do you think it has to be more of an isomorphic state?
Yeah, so you can ask the question, okay, so I mean, this is a deeper question. So all this, this RBB spin liquid stuff was based, like I said, it went back to stuff that Linus Pauling did on benzene molecules, right? And then you can ask yourself the question, do any of these simulations, even the DMRG ones, is it really a resonating valence bond spin liquid that they're actually simulating? The answer is actually we don't know. They're probably similar, but saying they're exactly the same, that's a far stretch. So these are sort of problems that people are still sort of struggling with. It looks like a spin liquid, it smells like a spin liquid. Is it really a spin liquid? It's hard to say, because the question is, when do you say that you've reached the thermodynamic limit, right?
Mm-hmm.
The DMRG simulations are done on finite size cylinders. The exact diagonalization simulations are done on 48 site clusters, right? The quantum computing simulation I showed you from Bert de Jong's group is done on 12 site clusters. We have a long way to go before we can actually say that we have some result that applies in the thermodynamic limit where you have many, many spins present. And then you can ask experimentally, do we have an experimental example of a quantum spin liquid in nature? And the answer is no. Despite lots of claims out in the literature, we don't really have something that smoking gun says that this material is a quantum spin liquid and is not something else. So this is also a very tough problem. And the reason why is in fractional quantum Hall effect, you're manipulating charge, and people know how to do that very well. And this is why you can show the fractional quantum Hall state has these fractionalized anyons. Very difficult to do that in the spin problem. It's much harder to manipulate spins than charges. It's much harder to prove that you have spin fractionalization as opposed to charge fractionalization.
Okay, thank you.
Yep.
Yeah, thank you again, Dr. Norman, for your
Thanks
great
a lot.
presentation. I really
You know
appreciate
where to find me if you have further
Thank you so much.
questions.
Thank you. Amazing
All right.
presentation. Thank you so
Bye-bye.
much. Appreciate it. Thank you. Okay, everyone. So